became involved in this. I became involved in this Greater Yellowstone Climate Assessment, which was an effort, which I'll explain a bit more as we go, but it was an effort to try to understand what do we know about the climate of this region in the past and where it's headed in the future. And so I'll just give you some highlights from that report, which we published last year, and it's available online at gyclimate.org if you'd like to read the document. The effort, the report was an effort, is a collaborative effort between the University of Wyoming, as well as the U.S. Geological Survey, Montana State University, and also the Greater Yellowstone Coalition. And so the kind of leads on the project are shown here. Steve Hostetler at the USGS did a fantastic role as kind of the lead author of the report overall, with the help of the rest of us. But he did a lot of work on the future projections. Kathy Whitlock from Montana State, who some of you may know, is a fantastic paleoecologist who's done a lot of work across Yellowstone and elsewhere in the West. She helped worked with me and my former PhD student, David Liefert, to add components to the report on the past climates of this region. And then Charles Wolf-Drimmel from the Greater Yellowstone Coalition led an effort to really engage with stakeholders around the region to try to better understand perceptions of climate change. And then Scott Biskey was our science editor, and he really kept us all in line, and we much appreciated that. So the goal of this was to create a sort of common resource for people across the region to think about what's changing, what has changed, and how might things change in this region going forward. And of course, this is a place where people have lived for over 13,000 years. There is a long history of climate change here, and a long history of people living with that climate change. And so, trying to help us all anticipate what's coming and think about how we can adapt and prepare for it and what choices we may want to make was an overall goal of this project. And just to explain again a little bit more about myself, and I'll show you a bit of this, is that I am a paleoecologist and paleoclimatologist focused primarily on the last 20,000 years or so. And I use sedimentary records. I use a mix of everything from geophysics to organic geochemistry to study how things have changed in the past. And this has given me this kind of long-term perspective on climate change. And this was a project that, to me, helped me try to better understand what's going on today. So the other part of this, as Cynthia mentioned, is that we've recently gained a building off the Greater Yellowstone Climate Assessment. The University of Wyoming recently was successful in obtaining a large grant from the National Science Foundation, which we call the Wyoming Anticipating the Climate Transitions Project, or WYACT. And its main goal is to try to help us as a university do a better job of helping communities anticipate and respond to the climate changes that are before us and the transitions that we may face. And so this project is actually a mix of everybody from atmospheric scientists to hydrologists to ecologists to geologists like myself, but then also social scientists and economists. And we're trying to work across these disciplines to think about how the various dimensions of climate change and its impacts, not just on the natural resources, but also on our social systems and economics. And so that we can help communities like Jackson prepare and think about those changes. So we just started this project, and I'll explain a little bit more about it as we go, but it really is sort of motivated by some of the findings from this Greater Yellowstone Climate Assessment, which hopefully I can give you some insight into today. So the goal of the assessment was to take this issue of global change and try to take it from this global issue that gets talked about in very general terms and think about what does it mean for our really specific landscape and ecosystem here. So, and this was in many ways one of the first efforts like this to zoom into a region, a smaller region, and to cross the boundaries of multiple states, different lands, whether they're federal, national parks or private ranches, tribal lands, all these different landscapes, and try to think about how are they being affected now and how may they be affected going forward. And we really broke the report out into trying to look at the different watersheds in the Greater Yellowstone area. So you can see the black outline up there, sort of centered on Yellowstone National Park, is the larger Greater Yellowstone ecosystem, or the Greater Yellowstone area. And then the thin black lines up there highlight the different watersheds that we focused on. There's 6 major watersheds in the Greater Yellowstone region. And what I'll show you tonight I'll highlight some of the results that are specific to the Snake Headwaters watershed here around Jackson. But to put this in context, the thing that's motivated this is that our climate is changing here. I don't remember. Some of you may have been here when I spoke about this. It may have been about 10 years ago now on a previous visit. I can't quite remember when that was. But I remember being in this room and speaking to this group about how things have been changing. And the update there is that we've continued to experience change. And this is just the average temperature for the whole state of Wyoming up until 2019, which happens to actually, incidentally, if you look at the orange line there, is actually one of the few recent years that was kind of had below average temperatures. But if you look at the orange line, it goes from this is based on weather station data from all across the state from about 1895 up to 2019. And, for most of that time period, the average temperature of the state was about 39.8 degrees Fahrenheit. And what's really changed is that since the 1980s, we've very rarely had years that were below average, below that average. And so, in fact, since 1980, there have really only been 2 significantly cold years, and they both followed global cooling. They're part of global cooling episodes that followed volcanic eruptions. So El Chichon down in Mexico erupted in 1982, and Mount Pinatubo in the Philippines erupted in 1991, and those led to cool years. And so if you didn't have those eruptions, we actually would have had a pretty extended streak of very warm weather since 1980 or so. But of course, it's not that the years are unusually warm. 1934 was actually the warmest year on record. It's just that we have had many more of those years. And so knowing that this is the context for what's happening in the state, we wanted to look at what's going on in this region. But let me dig into this particular graph a little bit more for you. And I just want to highlight the issue of kind of, the fact that there are many things always influencing our climate. Our climate is never stable, certainly over geological timescales. It's always changing. And that changes because we have changes in the sun. We've had changes in Earth's orbit. There are changes in the amount of dust and haze in the atmosphere. The volcanic eruptions, as I pointed out, can be really significant. And of course, we know things like El Nino in the tropical Pacific and other aspects of the state of the ocean. All of those things can work together to cause any given year to be warm or cold. And then, of course, on top of that, we're also always rolling the dice. There's just a lot of chaos in the climate system. So some years are warmer, some years are colder. And if we try to take these known factors that we understand and try to project how might our climate have changed over the last century, just based on these influences, we can actually do that. We know reasonably well what their relative effects would be. And so this blue line here represents just sort of the expected history of Wyoming's temperatures over this time period based on those natural influences. And you'll notice that it's kind of a smoother curve than the actual orange line, because there's also the chaos, the sort of random effect, so that you're randomly, by luck of the draw, you're rolling the dice, you're going to get a really warm year or a really cold year that's going to bounce around that blue line. But that doesn't explain why we've had such a string of warm years. Now, natural influences partially explain that. If you notice the blue line there at the end, does suggest that we should have had a relatively warm period, but not quite as much warming as we see. And so it turns out that a critical influence here is the fact that the amount of greenhouse gases in the atmosphere have been going up. And we know this is critical to the way that our system works. It turns out that these greenhouse gases, the way they stretch and bend, are really good at absorbing heat that's escaping from the Earth's surface. And I won't do this to you tonight, but sometimes I make classes of students, at least, or some audiences stand up and we'll go through the ways in which the molecules bend and stretch, which is kind of fun. But the important point is that the bonds in carbon dioxide molecules are just the right size that they absorb the wavelengths of heat escaping from the surface of the Earth and help to trap that. And if we take that added amount of insulation into account, you think about the CO2 is effectively like putting on a down jacket around the Earth. If we account for that, then we do a much better job of anticipating the changes in temperature that we've seen over the last 100 years. And so the black line here is the combined effect of greenhouse gas additions to the atmosphere because of human use of those, production of those gases, combined with the natural influences. And that is what seems to be required to explain the recent uptick in temperatures. And we know that that's not going away, it's going to continue. And so that was kind of the motivation for this Greater Yellowstone assessment, was to look at how might things continue into the future and what's really changed here in this Yellowstone region. So I like to think about it from this standpoint. I love this photo, Ansel Adams' photo from 1942, kind of classic view of the Tetons and the Snake River. And a really interesting question in my mind is, okay, it's fine, things are changing, the world is getting warmer, that's having various consequences, but what will that do to this view? How will that change this view? And what's, if you think about it, if you went out there right now and looked at the view, or, clearly this is a photograph taken in the early summer, if you look at the snow, if you went at the right time of year and looked at this view again, it would look mostly like it did in 1942. It hasn't changed dramatically, but the question is, will that change, or how will that change as we go forward? And what are the consequences of things getting warmer? What will that mean for this landscape that so many of us really value and cherish? Now, the greatest uncertainty about this going forward is really about our own decisions. We actually know quite a lot about the climate system at this point. There's been really intensive work. I mean, we've tried to study the climate system in many ways for over 200 years, just to understand from the standpoint of actually trying to understand ice ages. That's been a geological problem that we've worked on since the 1800s. And it was, in fact, studying that problem that led to the realization that adding greenhouse gases to the atmosphere would cause the world to warm. And so the first projection of that was published in 1896 by Svante Arrhenius, and he was setting out to understand the ice ages, but realized on the side that human activity would potentially also have this effect. So the greatest uncertainty here isn't our uncertainty about these essentially 19th century physics. It's actually about what will we choose to do and how much more greenhouse gases will be added to the atmosphere. So this graph here is going from, again, about 1895, but it goes all the way out to 2100. The black line is the changing amount observed of CO2 in the atmosphere. And this is measured in parts per million. So the scale here goes from 300 up to 1000. So roughly, if you imagine taking a big cube of air here and collecting, breaking that up into 1 million parcels, right now, about 420 of those parcels would be carbon dioxide out of 1 million. And that seems like a tiny, tiny amount, but of course we wouldn't have life on Earth without that. Plants wouldn't be able to photosynthesize, and the Earth would be frozen because that greenhouse effect is really vital to us. If we didn't have that insulation, we would be a frozen planet. But adding more is only going to make us warmer. And so the challenges here are looking out to the future. Will we stabilize the amount of greenhouse gases in the atmosphere, or will we continue to add quite a lot, or will feedbacks in the Earth system kick in that will also add more to the future? So what we decided to do with the Greater Yellowstone Climate Assessment was not necessarily focus on all of these possible scenarios going forward, but these 4 lines here, the 4 colored lines, are kind of 4 scenarios that the international scientific community and policy community have been using to help guide thinking about the future. None of them is likely to be exactly the future that we face. They just help us to imagine different scenarios. And so for the Yellowstone assessment, we focused on 2. And primarily we focused on the blue one there, which is where we have some mitigation of greenhouse gas emissions by mid-century. So we end up stabilizing our atmospheric concentration. But it's worth contrasting that with a scenario where maybe even with some mitigation, we end up with a very high concentration of greenhouse gases, because that is plausible. And it just helps to show what the consequences of our choices might be, to look at those 2 different outcomes. So I'm going to show you in some of the graphs going forward, I'm going to show you these kind of 2 scenarios. They're known as the relative concentration pathways, RCPs, 4.5 and 8.5, meaning those numbers relate to the amount of watts per meter squared that are additionally trapped by the gases. But you don't need to worry about that. You just think of these as some mitigation of greenhouse gases into the atmosphere versus essentially none. And we will look at the consequences of those 2 scenarios. So here's kind of the starting point to think about, which is, if you just took the average annual temperature across the Greater Yellowstone region, how would that change under those 2 scenarios? And so the black line there is the historic observed changes, and the blue and red lines are averages of many different simulations that various groups around the world have done on different types of climate models, and that we then have summarized for this region. And the blue, again, is where we have some mitigation of greenhouse gases by mid-century, and the red is where we don't have any. And what's interesting here is that if we look out towards that future, with some mitigation by the end of the century, we end up roughly raising the regional temperature here by about 7 degrees Fahrenheit on average as an annual average temperature. With no mitigation, we end up raising that to somewhere slightly above 12 degrees Fahrenheit. And I always think these numbers seem a bit abstract and hard to wrap our heads around. So this is where I want to try to provide some context here, but it's worth pointing out that there's some significant choices here that we have before us, because if you raise the temperature and have some mitigation, that keeps it at a fairly stable point, and it gives us time to adjust to that. Whereas if we have very little mitigation, the temperatures rise quite a bit, and we have much less time to adjust to it. And the temperatures rise almost double the amount. It's also worth pointing out that we are at the very beginning of that upward trend. So when we see, as we've seen in the last few years, very unusually high, strings of years with high temperatures, we're just beginning to experience what is projected to be coming here. Okay, but let's try to put that in context. I love thinking about this up here because our landscape here, the Teton landscape, is perfect context for this. Because when you go out there and walk around Jenny Lake or any of these places up in the Tetons that are shaped by glaciers, I always think of this as I'm a paleoclimate scientist, so it's like, for me, it's the equivalent of going and walking around the Acropolis in Athens. Instead of walking around in the ruins of some great ancient civilization, I'm walking around on the ruins of a colder climate. These landforms that are shaped here, that define so much of this landscape, were formed during the last ice age. And it's useful to know that when that ice age covered this landscape with glaciers and ice caps, that was a world that was, about 20,000 years ago, was about 5 to 7 degrees Fahrenheit colder than the kind of early 20th century. And so this is useful context, is to when I'm talking about warming on the order of 7 degrees, we're talking about an ice age magnitude change. I always like to kind of picture what that landscape would look like. So here's a picture from the bike path up there just south of Jenny Lake, right below the moraine there at Taggart Lake. And I just sort of sketched in these glaciers pouring out of the mountains there, as they would have done at the time, 20,000 years ago. But 5 to 7 degrees of Fahrenheit of warming was enough, of course, to melt that away and to allow forests to move up into those valleys. And so, we've been left with these really fascinating moraines and these beautiful U-shaped valleys as a function of that glaciation. And it's the 5 to 7 degrees of warming is what has translated that landscape of ice into the one that we all value now. So when I go back to this graph and look at these scenarios, where with some mitigation by mid-century, we warm by roughly 7 degrees, and with very little mitigation, we warm over 12 degrees by the end of the century, that is roughly in the ballpark. The some mitigation scenario is in the ballpark of the magnitude of change since the last ice age. And so this is, if you think about how much this landscape has been transformed since the last ice age, that is the type of impact, the scale of impact that we might face going forward, even with some mitigation. Now, that doesn't mean we don't want to mitigate, because of course, with no mitigation, we go back to the Eocene or the Paleocene, where there's crocodiles living in Wyoming and palm trees. So it's, hopefully we don't end up there. At least I'm not prepared to be there but later in my life. And I like to point out that if you look at when the blue line versus the red line crosses that 7 degree point, that lower dashed line there, roughly the magnitude of change of the last ice age, the blue line crosses it up to 50 years later. And so that gives us 50 more years to adapt to that change. So it's not that we're able to escape change. We're sort of inevitably going to have changes before us. In some ways, our choices, though, give us a chance to think about how much time do we have to mitigate that and to adapt to it and prepare for it. So just another perspective on this, and I like to think about it again from the recent geological past. 5 to 7 degrees of warming was what we experienced at the end of the last ice age. And so what I want to show you here are some animations I put together with some colleagues almost about 20 years ago now, but they're still valid animations. And what they show are, what you'll see here is each frame is going to be 1,000 years coming forward from 21,000 years ago. And it's just focused here on North America. The blue is the extent of the Laurentide ice sheet that covered almost all of Canada, came down to places like Des Moines and New York City, and it went all the way up to the Arctic Ocean. And then the coloring there, the shades of green, are based on fossil pollen records that we have, about 700 different fossil pollen records, mostly over the northern and eastern portions of North America. And it's shaded darker shades of green to show where spruce forests would have been growing in the past based on that pollen. And you'll also notice that North America looks a little bit different than it does today. Like if you look at Florida and the Bahamas and the coast off of New York, it looks different. And that's because we've adjusted the outline of the continent here for the fact that to put all that ice on the continent, you had to lower sea level by 300 feet. And so as we go through the animation, you'll see the forests move, you'll see the ice sheet retreat and sea level rise. And just to give you a sense of the total scale of transformation that 5 to 7 degrees of warming could produce. And I always think it's fascinating to imagine these forests shifting from, spruce trees, the boreal forest, shifting from growing in a place like Tennessee to growing all the way up in Alaska now. And if you look at this, I'll run it one more time. You can watch the coastline retreat as sea level rose. Hudson Bay is really fascinating because it's isostatically rebounding. It's the depression under that ice sheet. So it actually shrinks as sea level actually is rising everywhere else. The land there is actually rising because it's no longer being depressed by the ice. but all kinds of changes here. And so it's not just that the Teton landscape was covered by ice, but the wholesale transformation of sea level, glaciers and hydrology, but also our forests and ecosystems have been changed by what might seem like a relatively small magnitude change in our annual temperatures. Okay, so this brings me back to Ansel Adams's photo, and what I take away from sort of these initial things here is that our choices have a lot of potential to shape what the impacts will be. And some of those changes could be quite large. It's entirely plausible that we could not reckon, this was taken in 1942. If we go an equal distance into the future, we may really not recognize it in many of the same ways. I mean, of course, the physical topography will be the same. But as you'll see there, as I go forward, almost certainly one of the things we'll lose is all that snowpack that you see up there in the photo. And that, of course, will have consequences for the way the river flows, and it's likely that the forests would change. I think it's really interesting that back in the Miocene, these forests were somewhat similar, but there were elm trees and other eastern deciduous species mixed in here. And that's under a climate that's had roughly an equivalent kind of long-term mean state as where we are right now. If we were to sustain our climate of the last few years over a long period of time, that's the type of ecosystem that might be plausible. Okay, so we're only at the beginning of this change, but it's worth looking a little bit more in detail at what has changed for us. And I start with this photo of Jackson Lake because many of you, of course, are really aware that it does not look like this right now. This is the photo from the dock at the research station. And of course, if we went there right now, what you would see is a lot of, you actually do see the lake right there, but it's way down the hill. And there's a lot of exposed beach and cobbles. Not as much mud flat as in other areas, but it's still pretty dramatically different. So what is changing? So if we look at the weather stations around the Greater Yellowstone region since 1950, and just take the average annual temperature just for this part of the state and the region, our mean annual temperatures have risen by about 2.3 degrees Fahrenheit over that time period. And of course, you're always rolling the dice. Sometimes you're getting warm years, sometimes you're getting cold years. You can see those two spikes at the end of cold there from those two volcanic eruptions I mentioned earlier. But since Mount Pinatubo erupted in 1991, we've had quite warm years in a row. And so our temperatures have been climbing. This has had a significant impact on our snowfall. Now, this is the average across the whole area, so it's not. So you may say, well, I don't know if that's true here, and that's correct. Right around the Jackson area, it's actually not as dramatic a change as on average across the whole Yellowstone system. But because of warming, and particularly because of that warming that's causing snow to become rain in the fall and spring, what's normally on average across the whole region about 100 inches of snowfall every year has actually dropped by about 24 inches. So roughly a quarter reduction in the total average snowfall across the whole Yellowstone region since 1950. And there's an important caveat to this, which is that the weather stations are all below 8,000 feet. So the really high country may have a slightly different story. And I have looked at a few places where there is weather station data up high. And it turns out that for the same reason that warm air helps to melt snow and make rain down low, warmer air can hold more water vapor up high, and that becomes snow. And so there are a few places up high where you actually have almost a doubling of the amount of snow that's fallen. But unfortunately, that's over a very small portion of the total topography. Most of the topography is down low. And so there's only a few places that are really up high, and so it doesn't really make up for it. But there is undoubtedly this kind of downward trend in snowfall. And it's worth, again, also noting that total precipitation hasn't changed. It's just translated from snow to rain. And it's especially happened in the fall. So September, for example, has seen a 98% reduction in snowfall. But well, I'll get to the precipitation change. this has the constant, when you combine the temperature effects and the reduction in snowfall, this actually affects the stream flow. So this is taking all the hydrologic gauges across the whole Yellowstone region again and averaging them. And on average, back in 1950, peak spring stream flow would happen about June 14th. But as things have become warmer, the snow melts off sooner. And as there's less snow, it also melts off sooner. And so it's shifted forward in the year by about 8 days, so about a week. So now, it's instead of being the middle of June, it's the first week of June when you get that, on average, you get that peak runoff. This varies in place to place because, of course, we manage that water pretty intensively in a lot of places, but and it depends if you're up high versus down low on different rivers or creeks when this actually occurs. But it's pretty typical of all the streams that we looked at that there's about this week shift in the stream flow. Now, I said that precipitation overall hasn't changed, but it turns out that the total amount hasn't changed. Well, it's gone up slightly, which is interesting. But the biggest thing that's happened, aside from snow shifting to rain, is that we also shifted when during the year we're receiving precipitation. So since 1950, if you look across the graph here, each month is represented, and the bar there is just showing you the kind of average change in precipitation for each month. And you'll notice that the winter and summer months are both downward. They both are reductions in precipitation. So we're in the middle of winter and the middle of summer is drier than it used to be. But spring and falls are both wetter. And so those two effects kind of cancel each other out. But this is interesting in the spring because now we're shifting that snow melt earlier and we're adding precipitation on top of it. And that, of course, is what has led to the likelihood that we have increased flooding. And so here's just a photo from up by Bozeman of the floods this spring. And while that is, we can always have big floods. That's not an unusual thing to occur on a river system like that. It's also part of the pattern that we're seeing. And so these are just, again, the stream flows for each month from January to December for two different stream gauges on the Yellowstone River. And it's just showing the percent change in flow from kind of the last 30-ish years or so versus kind of more of the middle of the 20th century. And what you see is that peak, these big blue bars for May and April, May, and June, suggesting that we're getting more runoff during that spring meltwater time. But that also then means that all the water is flowed out of the system early, combined with the fact that we have less summer precipitation, means that through the rest of the year, July, August, and into the fall, you see the red bars suggesting we actually have up to 10–20% reduction in stream flow during those drier times of the year. So this is really important, of course, for the Idaho agriculture down the stream here. This is why they're calling the water out of Jackson Lake. They need that water to make up for that drier time of year. And at the same time, this, of course, has consequences for recreation around here. If you are a fly fisherman, though, there is a little bit of good news, which is that the kind of April early season fly hatch is actually kind of, we actually looked at this. It's actually drawn out longer, just the way temperature and stream conditions have changed. There is possibly some better opportunities to find that experience under the current conditions. But is this good for trout? I don't know. The lower flows later in the season and higher water temperatures, of course, are challenging to them. So these are things that have changed. These are observations. These are what the data show have changed since 1950. And if we just look out towards the future, then we can imagine that many of these trends would continue. But I'll just show you a few of the projections here. So again, I showed you these two projections, kind of with some mitigation or no mitigation, how temperatures might rise by either 7 or a little bit more than 12 degrees Fahrenheit by the end of the century. But what does that really mean? Like, what does that mean to us on the ground here? And I think a useful way to think about this is kind of more of the daily scale temperatures that we experience. So here's I'm just zooming into the information we had for Jackson and looking at these same projections for the future. This is a measure of the number of days per year where the average temperature is below freezing, below 32 degrees Fahrenheit. And so typically now it's about 250 days per year, where our temperatures are cold. And, it's a high elevation site here in the Rockies. This is why we have great snow. It's Wyoming, it's cold. But if you look at these different scenarios, that drops with some mitigation down to, below 200 days per year. And with no mitigation, it drops down to about 150 days per year below freezing. And so this is, several months worth of warmer than freezing temperatures, which I'll show you in a moment, becomes significant, especially when you start thinking about the snowpack on the ground. The other side of this equation is, what about the number of days above 90? And typically, numbers of days in Jackson that get above 90 degrees Fahrenheit is pretty small. It's not a large number. That's not very common. However, under these two scenarios, I always think this really, to me, captures the choices we have with these different pathways, where if we end up on with some mitigation, we end up with about 2 weeks of 90-degree weather every year over the later part of the century. But with no mitigation or feedbacks in the Earth system that add CO2 to the atmosphere because permafrost is thawing, things like that high emission pathway, we end up with 2 months of 90-degree weather every year here in Jackson. And that is a fundamentally different place than where we live now. Yeah, the library is closing. So this really highlights in some ways what's sort of masked by looking at those kind of just average temperatures only going up by, going up 7 to 12 degrees. The situation there is we're talking about 2 weeks versus 2 months of 90-degree weather. But when we went around and interviewed people for the report on what they were concerned about, the number one concern was water. And that relates to those temperatures because of how snow is impacted. And so here's a map of that Greater Yellowstone region again. The thick black line is the outline of the Greater Yellowstone ecosystem. The thinner lines are those watersheds again. The colors here show you areas where today we typically have winter precipitation falling as snow. That's shown in blue. And the other colors are where there's at least some mix of rain in there. And over the later part of the 20th century, beginning of the 21st century, of course, most of the high country, most of the Greater Yellowstone ecosystem was snow dominated, and it's a very snow organized system. And if you look at where we are now, there's some reduction of that, but it's not dramatic. But as we go forward, and these maps are based on that scenario with some mitigation, we just progressively lose. Even by 2060 to 2080, we lose most of that snow-covered high country. It becomes a mix of rain and snow across that landscape. And so if you think about the role snow plays here, from everything from providing water to the recreation opportunities it provides in terms of skiing and everything else, this is a real transformation that has the possibility of having pretty big impacts. And something I would point out here is that you see that blue area shrinking. Well, what that means is that the snow rain line moves up from being about 6,000 feet now up to being by this time about 10,000 feet. And of course, 10,000 feet is the top of the Jackson Hole Resort. So that is a big transformation in terms of the economy and social values of this ecosystem in this place. So this is another way of looking at that same thing. This is in the Snake headwaters. How many inches of water do we get from snow every year? Today, we get somewhere on the order of 10 to 12 inches worth of water out of all of our snow. With some mitigation, that drops down to about 5. And with no mitigation, that drops down to almost 0 by the end of the century. And so it's not that we're not going to get precipitation. It's just that Precipitation falling as snow has a lot more value in terms of water provided. And this has the potential to have all kinds of consequences, again, from like our water supply, but also think about combining this with 2 months of 90-degree weather. You can imagine the wildfire risk that goes along with this. So there's a lot of interesting consequences embedded here. And this is just a graph that I'll just run through quickly, but it just shows the peak in the runoff down the Snake River. The black line is where we are today. So this is by month, and it's the inches equivalent of water on the landscape moving down the river. The peak runoff is happening now in May and June, but the different colored bars there show how that moves earlier and earlier in the year, and the later summer flows go down as a result. So the change in snow has this big impact on the river system. So I'll just kind of wrap up here by saying that this is the point. This was kind of the launching point for our new project that we just got started, and which you may hear more about as we continue to work up here. But our goal in with this new effort that was funded by the National Science Foundation was to really help communities like Jackson think about how might we anticipate and respond to these changes? How do we prepare for them? And our goal is to bring together, we have roughly 20 different faculty who all have many students working with them and postdoctoral research scientists. And what we're trying to do is bring together that climate information that we have and match it with the information that we can gain about what are the impacts going to be, say, for vegetation, for streams and rivers, for our lakes and reservoirs, and then, of course, for people and economics. And one of the ways we're really hoping to approach this is not just do it in isolation at the university down in Laramie, but to be up here working with you and others and kind of bringing results that we have to you and talking with you and hearing your concerns and thoughts and iteratively evaluating this together so that we can make this be valuable information that you can use to help inform your decisions and help prepare for this potentially significant transition in this region. So what we really hope is that what we hoped with the Greater Yellowstone Climate Assessment was that it would launch discussions. And so we kind of feel like we need voices. We need to hear what are the impacts people are concerned about. What are the policies that we might need to be thinking about and evaluating. And so I'll just put, as I end up here, I'll turn it over to questions in a moment, but I'll just give you my questions to you we would love to know what are the potential changes that most concern you? What kind of projections about the future might be helpful? And what choices or policies are you thinking about that might shape the outcomes that we should evaluate and think about, try to figure out what their consequences might be. So I'll stop there and take any questions. But thank you so much for the opportunity to explain about this project to you.
So we have about 28 people on Zoom.
Okay.
Also, I've just asked Mike if we have any Zoom questions. I'm not sure if we do, so let's open it up to the audience here first.
Bryan, so when you shifted the snow lines basically in time, are you still assuming the same amount of total precipitation?
No, so yeah, so the question was when we were looking at that projection of how snow, the distribution of snow might change, are we assuming the same amount of precipitation? And we're not, we're actually letting the climate models project how total precipitation would change. And in fact, total precipitation goes up modestly over this time frame because a warmer atmosphere can hold more water vapor. And so it's not that we have less precipitation, it's just that it's warmer, so less of it falls as snow. And that snow melts off more easily. Yeah.
Repeat the question. My question is, when you say mitigation, some mitigation versus no mitigation, what demographic who's going to be doing the mitigating factors?
Yeah, great question. So the question for those on Zoom is, when I was talking about some mitigation of carbon emissions versus no mitigation, who's actually doing that mitigating? What's the assumption or consideration there? This is a global problem. The challenge here is that we're going to face these local impacts, but we locally only have a relatively small influence on that total amount of carbon being added to the atmosphere. And so this is certainly a global scale challenge. And it's interesting because it does require then many organizations, many countries, people all over the world to not necessarily collectively decide in unison how they're going to respond, but that their net effect is that there's some mitigation. And so what's assumed in that one scenario with some mitigation is that there is a significant energy transition that would take place on some global scale. And whether that's driven, it doesn't really specify necessarily how that takes place, except that it does assume a certain energy mix with a larger increase in renewables. And I believe it includes expansion of nuclear, but it does also include the assumption that there's some technologies that we're not currently using, at least at scale, that are brought on board. But it doesn't necessarily specify whether that's prescribed by governments or whether it's the market that drives it. And if you look at the changes that have taken place so far, where there is some reduction in we've slowed down the rate of emissions. That's mostly been driven by market forces. So it's possible that that would continue.
Our global environment emissions. So that can that be to average over the rest of the world? Large numbers of emissions, the small changes in our emissions would affect globally.
Yeah, so the follow-up question here was, if we make choices in North America that reduce our emissions, does that average out in a global way that is important? And absolutely. We are, of course, historically, the United States is responsible for more of those emissions than any other country. And we've done an amazing job of outsourcing emissions to China, so that China has really ramped up, but a lot of that is actually produced things that come back to the US. So, so our decisions, particularly in North America, but in the US, but across North America as a whole, have tremendous power in the global situation. And of course, even if it was only us deciding, that means there's that much less total carbon that's getting in the atmosphere. And it really doesn't matter where we stop it. We just need less total carbon in the atmosphere. And that could be, the three biggest sources, of course, are fossil fuel use, cement production, and forest clearance. And so you could change any part of that mix, and it would have consequences here. Land, like forest clearance. So the three again are fossil fuel use, cement production, and land clearance, particularly tropical forests. Clearance. There is roughly an area the size of Maryland every year of tropical forest that's removed, and that is essentially carbon added to the atmosphere, because you reduce the ability of those forests to store the carbon.
Just curious, do you know how forest fires do that?
Yeah, so forest fires are a good example of a feedback that could be part of the problem, where we could set policies and still end up gaining a lot of carbon in the atmosphere, because warmer conditions lead in more forest fires. I don't remember the numbers right off the top of my head, though, in terms of the magnitude of forest fire emissions. But they are meaningful. It's certainly a part of the equation. Yeah.
How sensitive are climate models with melting of Arctic ice?
Oh.
And, high rates.
Yeah. So the question is, how sensitive are these climate models to some of the feedbacks in the system? And the models that we're looking at here basically assume no feedbacks to the carbon cycle. they do include, and they absolutely represent quite well, the fact that there's intense climate feedbacks where you melt a lot of snow and sea ice in the Arctic. That causes the Arctic to warm quite a lot faster. So while we've warmed 2.3 degrees Fahrenheit since 1950, Alaska has warmed by 11 degrees Fahrenheit. The models capture that, but what they're not set up right now to do is incorporate, I mean, some models do, but the ones we're looking at don't incorporate the possibility that you would lead to methane clathrates being released, something like that. Or, the loss of carbon from permafrost to the atmosphere. That's one obvious point of concern. To me, actually, I find it somewhat encouraging that when we look back over the last million years, where we have ice core evidence of the amount of CO2 and methane in the atmosphere, and we have fairly good control in what we know about global temperatures, when we have slightly higher temperatures than where we are now during some of that time period, but we don't see evidence that we're getting a lot of methane released in those settings. Where you start to see it, evidence of it geologically is when you get back into the early Cenozoic, when things are meaningfully warmer. So there is potentially some buffer here before we kick some of those feedbacks off.
You might explain to everybody why that's so cool.
Oh yeah. So this is really important because there are these natural stores of methane, especially, which is an even more powerful greenhouse gas. And if you warm the ocean or you warm permafrost, you can release this essentially stored carbon into the atmosphere naturally. And that would just add more greenhouse gases, even beyond what we are adding to the system. And so that unfortunately creates the possibility of destabilizing things. And that's why that no mitigation scenario, while I don't think we're on any path societally to have no mitigation, it's still worth looking at because we don't know very well the likelihood that some of those feedbacks would kick in. Yeah, in the back.
Can you talk a little bit about the cement production issue?
Yeah, so cement production is an important source of CO2 because the way that we produce cement is that we take calcium carbonate from limestone and we actually burn it in furnaces to get the calcium out, that we then use to make new cement once you've added water to it. But what that does is it releases the carbon dioxide that was stored in that calcite into the atmosphere. And so it's not as large as the forest clearance or the fossil fuel sources, but it is, if you just think about the amount of cement we use every year, it adds up to be quite a lot of emissions. Yeah.
Mike Adler has a question.
Okay.
I don't know if we're gonna be able to hear him.
Yeah.
Mike, I can hear you if you say it to me.
Okay, very good. Yeah, you focused on the 4.5 mitigation strategy. You haven't mentioned the 2.6. Do you think that is totally unrealistic, that we'll never get there, like holding the temperatures at 2C level versus, or even less, versus, I think it's what the 4.5, quite a bit higher than, but that could have a very positive result, and it would change some of your projections that you were showing.
Yeah, this is a really good question. I will let me try to relay it to make sure everybody could hear. The question that Mike was saying there was, I focused on these two scenarios, the 4.5 and 8.5, but there is also this other scenario, which is shown in green on this graph, the 2.6 scenario. And that assumes that we stabilize pretty close to our current level of atmospheric CO2 and then begin decreasing it over the later part of the century. And so the question that Mike was asking is, do we think that's realistic? And of course, it's important because if we have the ability to achieve that, then the outcomes, the impacts that we're talking about are much less. The total warming that you get from that is significantly less. I mean, you just see how much lower the green line is in terms of CO2 in the atmosphere than the blue line even. So I'm not really optimistic about it personally, I have to admit, and I don't think our team was overall. I don't want to say it's not achievable, but if you look at the effort that's required, even to achieve the 4.5 scenario, we have to begin accelerating the use of new technologies and different strategies quite rapidly. I mean, the deployment of renewables required just to get to 4.5 has, solar has a footprint. In the United States, the solar farms required, it would be something equivalent to covering all of Massachusetts, Connecticut, and Rhode Island with solar farms. And wind at the same time would also have to end up covering an area roughly the equivalent of Illinois, Indiana, Ohio. And we'd have to basically be putting these out almost on a very high rate. I can't remember the exact rate of production that we need to get to achieve this goal. So it's not to say that we shouldn't strive if we thought it was plausible to go for the 2.6 scenario. It just is a much higher bar to reach, in part because we have to reach it much sooner, and we have to make those changes effective much quicker. And it's already quite challenging to think about how we would mitigate some of these things. But it is worth thinking that if we went after that goal, of course, we would really reduce the impacts. And so there's an interesting trade-off here, between how much impact are we willing to live with versus the sort of economic impacts or consequences of going through that type of transition. So it is challenging. And I'm starting to speak outside of my area of expertise here. So I don't want to overly sell any one of these scenarios one way or the other.
Yeah, I might just add another comment. I might just add, Bryan, another comment. There was an interesting article in the New York Times just a couple of days ago. They were pointing out that the technology advance is occurring very quickly, and potentially within, we've reduced the cost of photovoltaics 85% in the last 10 years. And the effect of all of that is that this article states that 90% of the people in the world will find that actually renewables are going to be as inexpensive as a dirty technology for new power generation. Anyway.
Yeah, this is a really good point. The point that Mike was making, if you didn't hear it, was that if you look at the rate at which the technology has advanced and the way the price has come down, it has changed dramatically. I mean, it's so much so that, of course, renewables really are competitive, and for potentially for a large majority of the world's population, the renewables will actually be cheaper than the existing technologies in terms of energy. So that change, that rapid acceleration of our ability to produce these things and make them economically viable is what opens the door to these scenarios like 4.5 and 2.6. And that is where there is some real hope that maybe we could achieve 2.6, but it's up against some of the other things that are roadblocks to actually producing large scale projects and changes in our energy systems.
Can I just hold your questions just for a quick sec? I've got a question here that came to me as a host via chat. So you want to read that for everybody?
The question is, there is a group of climate activists here in Jackson Hole that have put together our own recommendations for action going forward. May the Jackson Hole Climate Action Collective send you our projections and suggestions for going forward. I would love to hear those thoughts, and that is certainly the type of thing personally that our WYACT project would love to be, help engage with. And I don't know if you're directing that to Cynthia to share as well, but from my standpoint, please feel free to get in touch with me, and I will share my little secret with everybody that my email is bschuman@uwyo.edu, so universityofwyoming.edu. And the easy way to remember mine is that B Shuman also spells BS human. So look me up and feel free to send me questions or thoughts along those lines. Yeah, in the back.
So, quick question is, natural gas is kind of a generic name for methane.
Yeah.
Methane is more, a greenhouse gas. natural gas was considered at one time to be the transition fuel of the future. Any thoughts on that?
Yeah, so natural gas has played. So the question here is, the natural gas is just a brand name for methane often, and we use it in ways, that of course are contributing to greenhouse gases. So what's its role? It has played an important role because at least the idea is that when you burn natural gas, you burn it much more cleanly, and you get more BTUs out of it than when you burn coal. So for electric power production, when we transferred from coal-fired power plants to natural gas-fired power plants, that actually did reduce US and global emissions quite significantly. The catch to that is the fact that there are unfortunately leaks from the various well fields that are contributing that methane directly to the atmosphere. And so that part is not totally understood, except that when we did start producing a lot more methane or natural gas, we did see a renewed uptick in methane in the atmosphere. So, but we're not going to be able to make any of these transitions without having everything before us and letting everything be part of the mix. And so natural gas has played a really important role in terms of giving us the stepping stone to let a lot of the renewables come online, for example. In fact, right now, one of the interesting trade-offs of renewables is that we actually use a lot of fossil fuels to produce them. But we're using more natural gas rather than coal to do that. And that is valuable in the sense that it means less total production of methane or of greenhouse gases to the atmosphere.
Can I add to that? The easy way to think about it is when you're burning fossil fuels, you have your choices like coal, diesel, gasoline, and natural gas. And we're all dealing with what we call carbon chains. The carbon chains in coal are like 250 hydrogen, about 250 carbon. The only thing you get energy out of is hydrogen. So you get 250 hydrogen, you get all this carbon. You go to diesel, now we're down into 14 to 20 carbons and about double that in hydrogen. You go to gasoline and it's about a 7 equation. You go to methane, 1 carbon, 4 hydrogen. It's the most energy dense of all carbon fuels. This transition he just said about going in our power plants from coal to natural gas caused us to go from literally from about 2016 to now to where in the US from the electrical power generation, we're back almost to 1990 levels. Huge change. Big challenge ahead of us now is our transportation system.
So the leaks in
The
leaks in the system of the raw gas.
Actually, the industry has actually got a pretty big high effort. There's new sensors and satellites that have gone up that are specifically giving much better identification. And initially, quite frankly, this was shocked.
Yeah. So we see the influence.
Yeah. And so the industry, they realize they got to get their act together. But if we could figure out how to, how long is it going to take us to get the electric cars? So if we could get all the good old boys in pickup trucks to ship them natural gas as opposed to gasoline and diesel, they'd be moving us in that direction.
Electrolysis for impact.
Yeah, just for people online, if you couldn't hear that, just a really short summary there is that the difference between the different fossil fuels is the ratio of hydrogen to carbon in the molecules that we're burning. And if you're breaking carbon bonds that are between carbon molecules, you don't get much energy out of it. But if you break bonds with hydrogen, you get a lot of energy. And so by getting from coal, which is very complex organic molecules, down to methane, which is just a single carbon surrounded by hydrogens, you get a lot more bang for your buck. And so there's a lot of, and so effectively by switching to that fuel, we get a lot more energy for every amount of emissions we put in place. And while there are leaks and things like that that are concerned, there's actually a great economic incentive to get that under control, because that's fuel we're losing in the atmosphere that we could be, capturing and selling and using. And so there is an effort to get that under control. But the biggest transition is going to vehicles. Right now, almost all of our petroleum, like our liquid petroleum in this country, goes to the transportation sector. And if we electrify that, that allows us to potentially clean that up in the sense of at least using natural gas to produce electricity. Incidentally, then when you're driving your car, you're not producing heat and losing heat out of your engine. You're just using the electric motor, and that is much more efficient. So trying to get that, this is why we're trying to electrify the transportation sector, which could take place quite rapidly. Yeah.
So as a behavioral ecology,
Yeah.
I looked at the slope over the last 200 years of what I see. 2000. How many times in the past have you seen that kind of change?
Yeah, so it's a really interesting question is, how often have we experienced this type of warming, this fast of a rate of change before? And it's on a global scale, it's incredibly rare. We have very, very few geological examples where we just pour this much, we change the atmosphere this rapidly. There are some rapid events in the past, but they actually are more on the scale of this amount of warming over 10,000 years rather than over 100 years. So it's much more rapid. The end of the last ice age, you have this amount of warming, but it's over 15,000 years. So but on the regional scale, there are some places, like, for example, at the end of the last ice age, many of you might be familiar with the idea that there were these abrupt climate changes that took place around the North Atlantic. This was the premise of the Hollywood movie, The Day After Tomorrow, was that you could shut down heat transport of the Gulf Stream into the North Atlantic, and that creates rapid cooling. Well, it turns out those events near the North Atlantic had just either cooling or coming out of them warming, where you experience somewhere between 7 to 17 degrees Fahrenheit warming in 200 years. So quite comparable to this. And the optimistic thing about that is that people lived there when that happened, and they lived through it. And they did dramatically change their societies as a consequence, and the ecosystems survived. The species didn't go extinct; they just shifted where they live. So it's not. So I often think of this not necessarily as this is the end of the world. It's just a total shifting of the resources the way we're used to them, and it is doing it in a time frame where we experience it in our lifetime. Where it becomes challenging to adapt to that, especially when you think about infrastructure projects where you build it now, you're expecting it to last 25 years or longer. You have to, in a way, we have to think about what's it going to be like in 25 years when that project is really living out its full lifetime. So that's a major challenge. All right. Well,
one question. I look at our approach to climate change, and often wonder, do we understand how much greenhouse gas we create that really doesn't matter? Yeah, so how does that play against? And does anybody know how to say?
Yeah. This act.
Gas is a battery, and that battery might last 5 years, 10 years. I don't know if it is. You take it over the life of the car, it's fine.
Just try to repeat your question. The question here is, what are the carbon consequences of things like making lithium batteries, and how would that? What are the trade-offs here of shifting from fossil fuel use to these renewables, but where you use a lot of fossil fuels in that transition? That actually is something people have been studying really quite a bit. And it is the case that there is kind of a sweet spot there where you can't go through the transition too fast, or you end up adding a lot of carbon to the atmosphere. And you can't go too slow, or you end up relying on fossil fuels too long. And so then you end up adding a lot of carbon to the atmosphere. So there is kind of a middle ground, though, where that trade-off is minimized. And you do, and then eventually you do switch over to fairly clean sources enough that they become the energy sources used to produce things like lithium batteries. But of course, you know, I can tell you from just going down to the Atacama Desert where they're mining lithium, it's not free of other impacts. So it's you know, there's significant consequences. So there are going to be really tough choices to make in terms of thinking about how we manage this. And again, I just, you know, if I think about the battles that are already taking place over siting of wind turbines, for example, and think about how many more we would need to add to the landscape, this is not necessarily an easy thing to solve. But you're right that the transition is not completely free of carbon consequences in and of itself, and that's something we have to be mindful of. And there are other unintended consequences. For example, there has been some analysis of what if you put a price on carbon at, you know, say $50 a ton, and so therefore it becomes more economically valuable for farmers in the US to grow trees than to grow corn or wheat. And all of a sudden the whole Midwest becomes a forest plantation. That's bad enough from our food standpoint, but it takes so much water that it actually drops the Mississippi River water levels. And we're already at low levels right now. So there are a lot of trade-offs here. There's this kind of nexus of issues where we have the interaction between climate change, our energy, our water, and our food. And how we balance those different trade-offs is something that's difficult. And that's why it's a huge problem, very challenging to take on.
A quick question for you, Bryan, is how close are we to that sweet spot you mentioned in terms of producing new renewables versus you know, going too fast and producing too much pollution?
Yeah, so Mike was asking how close are we to that sweet spot of that transition in terms of producing renewables. I believe that we're pretty close to it, but I don't remember the numbers directly off the top of my head. It's worth looking at. I know there has been some really interesting work on that topic, but I think we're not currently like exceeding that. In fact, we're still quite slow compared to where we need to be. But I can't remember how close we are to that line. So it's, yeah, I'm sorry not to remember the details there.
This
Cynthia.
is probably outside of your interest.
Yeah.
But my concern is that as we continue to see the shift in the patterns of snow and less snow storage and then less stream flow in the summer, how is that going to play into the legal calls that, for example, Idaho has on us and other downstream states on the Colorado River?
Yeah, so Cynthia's question is a really important one, which is as we reduce our snowpack and change stream flow and we have lower flows later in the season, how does that interface with our legal agreements between states and other users about water? And as you may know, the Colorado River system is kind of the classic example where back in the 1920s, they allocated the river in fixed amounts, not percentage of flow, but actual fixed amounts of water. And they happened to do it in 1920, which as far as we can tell was the wettest decade in the last 1,000 years. And so it was a really bad time to set it in a fixed way. And that's why Lake Powell, which sits on the Utah-Arizona border, was in part just make sure there was always a supply of water that was legally allocated to the lower states, the southern states there on the Colorado River system. But now that reservoir is running dry. And so the Colorado River system is the classic example where we're almost inherently going to have to renegotiate that. And that is going to be very challenging. So up here, the Idaho of course, has the first right to the top 40 feet or so of Jackson Lake. Yeah, it's it's a lot of water. And so the question is there some way to bring uses in this region into that equation? And this is something that is actually a topic that the Y-Act project is interested in engaging on. Is not that we have any role in changing that legal agreement, but can we change the way it's sort of practiced in some way to help ensure that just because Idaho needs the water, that there isn't all the costs that come along with the reservoir being super low here. That is something that's is actually one of our first projects that we're going to do, is to do a set of simulations of different scenarios of water flow on the upper Snake River and what that means for the lake, but then also what it means for fish and then other recreational uses and economic consequences. And there's interesting issues also related to how the river interacts with groundwater in the valley here. And so it's worth exploring those consequences as well. So there's not necessarily an easy solution to the legal situation, but maybe there's some ways to negotiate how that is actually practiced. But I know there's a lot of people, at least on the Wyoming side of the line, who are very eager to work on that issue. But there's no doubt that changing our hydrology, because we're changing our snowfall, is only going to make these types of problems more acute. And it's not just here on the Wind River and the Bighorn River side. We go to the Supreme Court routinely over water with Montana. On the Platte River, we go to the Supreme Court routinely with Nebraska. So this is across the region. It's something we're going to continue to face. And I'll just say, you may be aware, like the Powder River in northeastern Wyoming has historically run dry. Like it's an ephemeral system that often doesn't flow. But under many of these scenarios for the future, it's quite possible that some of the other rivers, not necessarily the Snake, but some of the other rivers in the region could also move into that state. And that would be fundamentally different. Although we do think it actually had precedent in the mid-Holocene, which was much more arid. So it's interesting. That's my own interest, is looking back at that geological past as a way to have some analogs to help us think about what we might face.
So I think you probably need to think about getting farmers in your Wyoming.
Oh, absolutely. Actually, there's actually a significant agriculture component. So we have on the UW side, we have people who are part of the UW Agricultural Extension Service involved, as well as some of our ag economists. And part of our project is working with ag producers and users of water. It's interesting, though. I mean, water use is really variable. So we're going to focus on 3 main watersheds for this project: the Upper Snake, the Upper Green, and the Wind River. And each of those watersheds has very different uses in terms of water. Recreation is really important up here, but the Upper Green and especially the Wind River, agriculture is really a big deal. Yeah.
You never really mentioned population.
Yes, population growth. Yeah, so population growth is it's certainly, every time I drive down to Denver and sit in traffic, I think, oh my gosh, we have an issue. But the so the way I always think about this issue is, so the question was, how does population growth fit into this? And it absolutely does. And you think about the climate impacts, they are the consequence of population size times use of resources. And so you could grow the population really large if you kept the use of resources small, or the carbon emissions small. The flip side is, if you want to have carbon emissions very high, it's better to keep the population small. And so one of the challenges in the United States is that our use of carbon per person is just tremendously higher than anywhere else in the world. And so from our standpoint, our best contribution would be to reduce the emissions and the resource consumption. But globally, it's not insignificant that the population continues to grow at its rate. So that's globally a factor. But then it also, of course, as you all are probably very aware, locally, this is also a big deal as well, because how we respond and adapt to these impacts locally is going to interface quite directly with how the population grows regionally, not just in terms of numbers of people who are permanently living in this area, but even the numbers of people that are coming to visit. So let's say Lake Mead and Lake Powell down in Utah and Arizona dry out. Well, now you all of a sudden you have all these boaters who want a lake to go, out on, and they're going to come up to Jackson Lake. So there are actually interesting ways in which climate change in and of itself may impact some of the local population pressures. And so this is something that we're actually quite interested in thinking about, or what are some of those trade-offs that we need to keep in mind locally that are the kind of indirect effects of climate change that we may not even be thinking about. And so I know it's not a perfect answer to your question, but the population effect here is really meaningful. And I'll just end my answer to that question with the anecdote of that doesn't apply here, but is a meaningful one of a hurricane impacts along the coast. On the East Coast, you have had this increase in the intensity of storms that are making landfall, and that has increased damage, which has had a lot of economic and, of course, tragically human life consequences. But that's made worse by the fact that the population along the coast has grown, and simultaneously also has built more houses and has more things in those houses that are in the pathway of those hurricanes. And so out here, it's not hurricanes, but you could think of it as wildfires and things like that. And so there is certainly this interface between population growth and climate change. All right, yeah, thank you very much. It's great to have this chance to chat with you all.
We do have a small gift for you as a speaker.
Oh, thank you very much.
A little geologic
Oh, all right. Should I look at it?
geology there. Yeah, you can
Yeah, good.
can show it to the Zoom audience. You can get it out of there.
And get it out of the bag there. Excellent.
Okay, yeah. Thanks, everybody, for putting your chairs away in advance here.
No.
And you can turn your cell phones back on now.
Oh, fantastic. Wow.
There's a note explaining what it is.
Great, awesome.
So yeah, so
Where is it from?
I think it's from Florida.
Oh, wow. Oh, interesting.
Fossilized.
Yeah.
Agate or
Yeah.
agate.
Yeah, wow. So neat. Thank you so much. That's great.
Yeah. All right, thanks
Thank you,
everybody on
everybody.
Zoom.
All right. Great talk, by the way. Fantastic talk. I really enjoyed it. I just said it was
Oh,
fantastic.
thank you very much. Yeah.
I give talks on the same topic, but your focus locally here, and it was fascinating for me to hear all of it. You may have missed it. I was just saying,
Happy to share. Sorry, there's a lot of chairs being moved in the background here. It's making it hard for me to hear.
I gave a talk on global warming and what have you in January of this year here. So I have a lot of information, together for this same, on the same topic. But your talk in particular, focusing on the regional, region here was fascinating.
That's what we've really tried to do. Is focus.
Ready?
Yeah, well, it'd be great to chat with you more if that'd be useful. Or I'd love to hear your thoughts on it. So.
Yeah, well, in fact, if you, I'd be happy to send you my presentation, make it available to you if you're interested. And I'd be very much interested in.
Yeah, that'd be wonderful.
Yeah, if you can make yours available, that would be fantastic.
Yeah, I absolutely can make this available to you and to others. Yeah, that'd be great.
And
All right,
if
thanks.
you get something from those people that have their suggestions, could you send it to Cynthia and I?
Yeah, absolutely. Yeah, I will share if I get other things. Yeah, I'll share them for sure.
Hey, Mike, I was reading your article today, and I'll talk to him a little bit more over lunch, over dinner with him about that.
Yeah, I
new
brought up
study
one
that you
aspect.
put up there.
Thanks. I brought up one aspect of that having to do with the photovoltaics that came out in that article. So it's a very interesting article.
Yeah, what the cost of photovoltaics was down 80% and wind was down 55.
That's right. In the last 10 years. In the last 10 years.
Exactly.
I'm gonna have to turn the Zoom off.
Oh,
so
okay.
my computer can
All
harass
right.
me.
Yeah, no,
All
that
right.
makes sense.
Oh, I know.
Good enough. Thanks, Mike.
Thanks, Mike. We're gonna get
Yeah.
shut off here on Zoom.
All right.
But I'll send you some related stuff. That would be great.
Good.
Okay, yeah.
I'm gonna start
Okay.
taking your
Bye.
clothes off. No.